The National Electrical Code, specifically Section 250.52 FR, addresses ground ring electrodes. This section stipulates that a ground ring encircling the building or structure must be in direct contact with the earth. It should consist of at least 20 feet of bare copper conductor, and the conductor should not be smaller than 2 AWG. The question arises whether the 20 feet of copper must form a complete loop entirely around the building to be code compliant. While the code itself may not explicitly mandate a complete loop, it is a very common installation practice to do so. To ensure compliance and avoid potential issues during inspection, it is advisable to seek local interpretation from the authority having jurisdiction, commonly referred to as the AHA. This could be a local building inspector or electrical inspector, as their interpretation of the code is what ultimately matters in your area. It's always best to confirm local requirement. The primary purpose of the grounding electrode system is to provide a low resistance path to ground for fault currents. This low resistance path is crucial for safety, allowing protective devices such as circuit breakers and fuses to quickly clear faults and prevent electrical shock hazards. A ground ring electrode, when properly installed, contributes to this low resistance path. The ground ring should be buried in the earth around the building. This ensures a large surface area contact with the surrounding soil, which helps reduce the resistance to ground. Whether the 20 feet of copper is buried in a complete loop or in a different configuration is unlikely to make a substantial difference in the overall resistance to ground, assuming equivalent burial depth and soil contact. The difference in resistance would probably be negligible. Soil composition, moisture content, and the depth of burial are much more influential factors affecting the ground resistance. These factors significantly impact the effectiveness of the grounding electrode system. However, adhering to the code and local interpretations as closely as possible is always the best practice. Code compliance demonstrates due diligence and helps ensure the safety and reliability of the electrical system. Consider that NEC 250.4 outlines general requirements for grounding and bonding, emphasizing the creation of a low impedance path for fault current. This section explains the overall goals of grounding and bonding in electrical systems. Furthermore, NEC 250.50 discusses grounding electrode systems and requires that all grounding electrodes be bonded together to create a unified grounding system. This interconnection ensures that all electrodes work together to provide a low impedance path to ground. In addition to the ground ring, it was mentioned there are two ground rods. NEC 250.53 A3 permits the use of rod, pipe, and plate electrodes. The code specifies requirements for their installation, including minimum depth and spacing. If using multiple rod electrodes, they should be spaced at least 6 feet apart. This spacing helps to minimize the overlapping of their effective grounding zones. Supplementing the ground ring with ground rods can further improve the overall grounding system performance. The combination of a ground ring and ground rods creates a more robust and redundant grounding system. When installing a ground ring, consider the following best practices. Firstly, use bare copper conductor of the correct size, at least 2 AWG. Secondly, bury the conductor at the appropriate depth, typically at least 30 inches below the surface. Thirdly, ensure direct contact with the earth along the entire length of the conductor. Fourthly, properly bond the ground ring to other grounding electrodes, such as ground rods, using appropriate bonding connectors and conductors. Fifthly, document the installation thoroughly, including measurements of ground resistance, if required by local codes. Sixthly, consult with the local authority having jurisdiction to clarify any specific requirements or interpretations. Regarding ground resistance, while the NEC does not specify a maximum ground resistance value for a single electrode, it is generally recommended to achieve a resistance to ground of 25 ohms or less. This is outlined in IEEE Standard 142, also known as the Green Book, which provides recommended practices for grounding of industrial and commercial power systems. If the initial ground resistance is higher than desired, additional grounding electrodes may be required to lower the resistance. The effectiveness of a grounding electrode system can be influenced by several factors. Firstly, soil resistivity is a major factor. Soil with high moisture content and dissolved salts tends to have lower resistivity, making it a better conductor. Secondly, the type of soil affects resistivity. Clay soils generally have lower resistivity than sandy soils. Thirdly, the depth of the electrode affects its contact with the soil. Deeper burial typically results in lower resistance. Fourthly, the surface area of the electrode in contact with the soil is important. Larger surface area provides more pathways for current to flow into the earth. Therefore, careful consideration of these factors during the installation can help optimize the performance of the grounding electrode system. It is also crucial to use proper bonding techniques throughout the electrical system. Bonding ensures that all metallic parts are electrically connected, creating a low impedance path for fault currents. This helps to minimize voltage differences between different metallic parts, reducing the risk of electric shock. NEC 250.92 outlines the requirements for bonding service equipment, including grounding electrode conductors, metallic raceways, and enclosures. Proper bonding is essential for creating a safe and effective electrical system. Also note that NEC 250.64 covers grounding electrode conductor installation. It specifies requirements for the size, routing, and protection of the grounding electrode conductor. The grounding electrode conductor connects the grounding electrode system to the service equipment. This conductor must be sized appropriately to handle the available fault current. The code provides tables and guidelines for sizing the grounding electrode conductor base and the size of the service entrance conductors. It is essential to follow these guidelines to ensure that the grounding electrode conductor is adequate for its intended purpose. Additionally, NEC 250.68 and 250.70 cover connection to electrodes and methods of grounding electrode connection, respectively. These sections outline the acceptable methods for connecting grounding electrode conductors to grounding electrodes. Connections must be made using listed connectors suitable for the purpose. The connectors must be mechanically secure and provide a low resistance connection. Improper connections can compromise the effectiveness of the grounding electrode system. When installing a ground ring, it is important to coordinate with other trades to avoid conflicts with underground utilities or other structures. Before digging, always contact the local utility companies to locate any underground lines. This will help prevent accidental damage to utilities and ensure worker safety. Also, consider the potential for corrosion of the copper conductor. In corrosive soil environments, it may be necessary to protect the conductor with a suitable coating or wrapping. The choice of protection method will depend on the specific soil conditions and the recommendations of the conductor manufacturer. Another important consideration is the potential for ground settlement. Over time, the soil around the building may settle, which can affect the integrity of the ground ring. To mitigate this risk, it may be necessary to provide some flexibility in the conductor installation. This can be achieved by using a slightly longer conductor or by incorporating expansion loops in the ring. Regular inspections of the grounding electrode system are recommended to ensure its continued effectiveness. Inspections should include checking the condition of the conductor, connections, and ground rods. If any signs of corrosion or damage are found, repairs should be made promptly. Ground resistance measurement should also be taken periodically to verify that the system is still performing adequately. In summary, while the NEC doesn't explicitly state that a ground ring must be a complete loop, it is generally considered best practice to install it that way. Always consult with the local AHA for specific interpretations and requirements. Focus on achieving a low resistance path to ground by carefully considering soil conditions, electrode placement, and bonding techniques. Finally, regularly inspect and maintain the grounding electrode system to ensure its long-term effectiveness and reliability.